Yep, looks like we're live. All right. Well, welcome everyone to another episode of GPU Mode. Today, I'm really thrilled to have Joe Fioti here, who's going to be talking to us about something pretty different, which is his project and company Luminal, which is you said a project I've been following that has a different approach, where instead of writing kernels, you search for them. I figured it might be a big interest to people used to compiler-based approaches, and so I was pretty excited to have Joe come on. So yeah, Joe, please, without further ado, please go ahead.
All right, everybody. Hey, everybody. I'm glad to be here. Yeah, we're Luminal. My co-founders and I made Luminal, and it's basically an ML compiler, and we take a search-first approach. So there's some other ones out there now that are, I think, more recently trying to use LLMs to generate kernels. We're more of a traditional compiler route, where it is a deterministic code gen compiler. Yeah, I mean, initially I started it because I wanted to run LLMs on my laptop really fast. And it does that now, but a lot of people in the community started using it for cloud. And so we've spent a lot of effort getting this to run well on cloud as well. And, really, I think that the whole sort of title of this talk is radical simplification through search. And I think that really that is the overarching goal here, that the ML ecosystem is pretty complicated, especially at the low level. You have CUDA, cuDNN, cuBLAS, Nickel, libtorch, PyTorch on top of that, transformers on top of that. And that's only in the CUDA ecosystem. And so it's just a very fragmented approach. It relies on a ton of handcrafted kernels and everything, which are very labor intensive. And so, we set out to see if we can get a compiler to automate a lot of this stuff. And so, yeah, I'll jump into the slides here. I think everybody should be able to see these slides. Yeah, so fundamentally, I kind of came at this from a first principles approach. And I thought what are neural networks? What is deep learning fundamentally? And, everybody knows that it is mostly just linear algebra. And it's very simple linear algebra, in fact. And so if you can basically handle scalars, vectors, matrices, tensors, n-dimensional tensors, and then do some simple operations on them, you can handle most neural networks out there, most at least relevant neural networks that people are using today. And so basically, yeah, those are the primitives of our library here. So if it is so simple, though, why are the existing solutions so complicated? Well, PyTorch has something like 1,200 operations, and it supports, I think, 15 different data types now, and it runs on all these different devices. And so, CPUs, different types of GPUs. I think it does run on TPUs. I'm not sure about Neural Engine, maybe with Core ML. But basically the number of implementations that you need actually scales multiplicatively as you scale up these different things. And so it's not number of ops plus number of data types plus number of devices. It's number of ops times number of data types times number of devices. And so you just get this massive explosion in complexity, where it's for every new op you add, you have to support it on all these different data types on all these different devices. And for every new device you add, you need to support all the ops and all the data types, and et cetera. And so, it ends up being, I think PyTorch is over 3 million lines of code now, and TensorFlow is worse. And so really we came at this and said, how can we do all of that in ideally 1/100th the complexity, and at least 1/10th. And so, yeah, like I said, we come at this from a first principles approach, and we said, what operations do we absolutely need? And so we built Luminal just to use these 12 operations here. And so actually these are 11 here. And so basically we have on the left-hand side here, the unaries. So these are basically unary operations that just operate on a single tensor at a time. And they just do an element-wise operation. So we have exp2, log2, sine, recip, and square root. And then in the middle column, we have our binaries. So these take in 2 tensor inputs and produce 1 output. Add, multiply, modulo, and less than. And then we have our reduction ops, and we only have 2 of them. So we have sum reduce and max reduce. Basically, you just reduce one dimension of your tensor by taking either the sum of all the elements on that dimension or the max of all the elements on that dimension. And it turns out this is basically all you need. You can build like LLMs, you can build mixture of experts, you can build diffusion models, all of this with just these operations. So we basically build like very complicated models and very complicated operations just by recombining these simple operations. And so this keeps the core of our library very simple. So you didn't even see subtraction on this list of operations, because subtraction is just multiplication and addition combined. So you can, instead of doing a minus b, you can do a plus -1 times b. Same with division. As long as you have reciprocal and multiply, you can do division. And mapmul is a little bit more tricky, but as long as you're able to broadcast tensors and then sum reduce them, all you really are doing in a mapmul is you are doing a broadcasted multiply and then a sum reduce along the k dimension. And then a convolution is just, as long as you're able to track shapes, you can do a pooling operation and then do a mapmul with the kernel. And so, yeah, these are the fundamental core operations that everybody expects a ML library to have, and we don't have them because we're able to just use our simple ops to do them. So the other, I would say, reason why modern ML libraries are complicated is because they are very dynamic fundamentally. This was one of PyTorch's big selling points, is that they would be super dynamic and nothing would be static, and you'd be able to modify anything you want at runtime. And that's great for development. There is a pretty significant performance hit and complexity hit that you take once you commit to going full dynamic. And so what we've actually done is we've taken the opposite bet, and we said that, you know, these models, once you specify them, are super static. They're basically just data flows through this graph of computations, and then those graphs don't change. Maybe the weights change, certainly the activations change, so the actual data flowing through changes, but the graphs themselves don't change. And so we can specify all these modern neural networks just as these directed acyclic graphs of computations here. And so, you know, in front of us, right in the middle here, we see what would be basically a mapmul. So we load in the tensor as one of the inputs. We load in the weight for that layer as one of the inputs. We do our broadcasted multiply, and then we do our sum reduce, and that's it. And then on the right-hand side, you can see, I believe, I want to say that is a transformer layer. It might actually be a subset of a transformer layer, but it's, you know, you can see that these graphs can get quite complicated. And then, yeah, once you specify out like a full language model, it's like so massive that you can't even see individual nodes anymore. So the consequence, the main consequence of taking this pretty different approach is that our core library is actually extraordinarily simple. The entire core library is under 5,000 lines of code. I expect it'll stay that way. But it's not fast, because if you're doing, instead of a subtraction, you're doing an addition and a multiply every time you want to do a subtraction, that's obviously going to take a performance hit. And you know, if you're doing a ton of maybe like 10 or 20 different primitive operations just to do one complicated operation, there's obviously a performance hit. So the first time I ran Llama 7B, I had to wait all night for it to generate one sentence. So it was like about 2.5 hours per token. It was, yeah, not breaking any speed records, but that's okay. You're not meant to run these graphs of primitive operations. The point is that all of this is really setting us up so that we can compile our way back to speed. And because we're dealing in primitive operations, it's much, much easier to write a compiler for our representation than it is for a much more complex representation like you would have in, say, PyTorch. So here's another view of the sort of simplification that we're working towards. Traditionally, again, you'd have like Hugging Face transformers on the top, and then that would sit on top of something like Xformers and PyTorch, which themselves sit on top of like libtorch and all these handwritten kernels. These handwritten kernels would then use like cuDNN or cuBLAS, and then that sits on top of course, raw CUDA. But since we are directly generating CUDA kernels, you basically are using Luminal, and then you have CUDA right beneath it. And you know, we're working on developing a PyTorch backend, and so you can you can keep your PyTorch code if you really want to, and then you could basically, PyTorch would just call Luminal instead of calling libtorch. So like I said, yeah, Luminal is slow by default. We're using these primitive operations, but we're not meant to actually run those primitive graphs. So what we do is we transform those primitive graphs into much faster graphs. And what would we call a program that transforms a very slow high-level representation into a very fast low-level representation? Well, you'd call them compilers. And so most of our efforts are on building a really, really, really great ML compiler. So we're not the first one, though, to come up with the idea of using compilers for machine learning. Certainly compilers have existed for a very long time in general programming. But I would argue that the amount of complexity expected in your input program directly translates to exponential complexity in your compiler. Because as you're, take a just general purpose programming languages, you can basically specify any possible computable program in these general purpose languages, which means the compiler needs to be able to deal with any possible program coming in. So I'd argue compiler complexity scales with the complexity of the assembly coming in, or the assembly that is produced squared, or maybe cubed or something. And really in the ML world here, we're going for peak performance. I've worked in hardware for a long time, and to get really peak performance, ideally you want as simple of hardware as you possibly can have. So you want everything to be statically scheduled. You want everything to be decided ahead of time by software. This is one reason why CPUs don't perform all that well with ML. It's because they are extremely complicated pieces of hardware, because they can't really assume very much about their software. So the more complexity that we can push into the software, the less we can push into the hardware, the more hardware we can dedicate just to computation. So we want, again, static scheduling, static allocation, static prefetching, all that stuff. And this sort of boils down into a hardware architecture known as VLIW, very large instruction width. And so there are, legacy systems that have tried VLIW in the past. The most famous, I believe, is Intel Itanium. Tried it, I think, in the 90s, and it didn't work out very well. Now, I would argue that the main reason for that is because they were a general purpose CPU trying to do this VLIW stuff. And again, like I said, if you're dealing in the world of general purpose computation, your compiler is going to need to assume nothing about the input. And so your compiler is going to be extraordinarily complicated. And that's one of the reasons that Itanium failed. So that is the standard VLIW paradox. The compiler just needs to be way, way, way too complicated. So our core insight here is we've seen how other teams have solved extremely complicated problems in the form of games. And so AlphaGo, for instance, is a pretty interesting example where the developers of AlphaGo were not these Go super geniuses. They weren't these amazing Go experts. But what they were able to do is program a machine to search through all of these different Go states. And they basically posed the Go problem as a search problem. And so we thought, what if we treated the GPU kernel compilation problem as a similar type thing, where we are searching, instead of searching through game states, we're searching through the space of logically equivalent GPU kernels. And that way, we don't really need to be super clever about our heuristics or rules that we set up in advance. We can basically just search through every decision that we have to make. So what is the correct size of this tile, or is it good to unroll this loop or not? I don't know. Our answer is we don't know. Let's search through all of them. And so search really eats up this complexity in the compiler. So what we do, our approach is we represent these models as these compute graphs. And then what we do is we take the compute graphs, we convert them to what's called egg log expressions. We'll get to egg log and what that allows us to do. We use these rewrite rules inside egg log to transform this expression and build out this big search space. I think we have a pretty unique way of storing this search space. We use this thing called an egraph, but we'll get more to that later. And so we build out this supermassive search space. The search space can have potentially millions of possible kernels in it. And then what we do is we actually go through and we generate all of the different kernels in the search space, and then we profile all of them. It's really straightforward and simple. And it depends how big your search space is, but you can get really fancy here, and you can use things like MCTS to prune down the search space tremendously. You can use stuff like beam search. We're actually looking into using some learned guided search in a similar way that like AlphaGo used. But the simplest way to pose the problem is we're just going to do brute force search. So we have a little bit of a demo here to sort of show that search process. We just launched it this morning. But yeah, we have you can just choose from a number of different possible kernels here. Let's just do the square matmul here. And then we will hit compile. And what it does is we can see some of these rewrite rules or descriptions of rewrite rules going here. And we're building out this search space here. And then we get a ton of these different logically equivalent kernels. But as you can see, the kernels themselves structurally are quite different. The only thing that really matters is that they do produce equivalent outputs. They do still produce the correct outputs. Some of them might be faster, some of them might be slower. And so what we do here is we keep track of the best performing kernel, and then we go through a whole bunch of candidate kernels here, and we measure how long they're taking to run. And so we track that best performing runtime over time, and then we get out an output. And so once it's done compiling here, we will get our output kernel. There we go. Yeah, that's our little demo there. You can go to demo@luminalai.com and try it out. But it's just supposed to be a simple visualization of the process going on. So yeah, that's that. And then, so what is actually going on in the back end to search through all of this stuff? Well, we have this thing called an intermediate representation. It's pretty standard for compilers to have. And what our IR looks like is these graphs here on the left-hand side. And then we have the actual generated kernels sort of as a direct translation of what this IR turns into. And so, we have a very simple computation here. We take in a vector of 10 elements, and then we want to exponentiate all of the elements and then take the sign of all the elements and then save that as a output vector. And so what we do is we have a global memory pointer at the top here. It's pointing to some memory in global memory. And we basically have a loop in, which says that we're going to loop for 10 times. And Z in this case is the stride, the stride. And so basically you can think if you have a for loop and that for loop is stepping through elements, Z would be your iterator. And so because our stride is Z, basically as we iterate one by one, we aren't multiplying our iterator by anything. And so we're just stepping through single elements at a time. If it were Z times 2, we would be stepping through every second element. But since it's Z, yeah, we're just visiting every element sequentially. And then once we're inside loop in, we do an exp, and then we do a sign, and then we do a loop out. And our loop out also has a stride, and that basically tells us how should we step when we're saving our elements back to global memory. And so this allows us to do extremely complicated schemes where we're loading transposed matrices, or we're loading just very complicated access patterns. We can load a matrix, we can do some computation on it, and then we can save it in transposed form, all by just manipulating strides here. But yeah, on the middle area right here, this is what that kernel actually looks like when generated into CUDA. And so basically, yeah, it's just a standard CUDA kernel, and we pull in A and B, and basically A is our input and B is our output pointer. And so then we get our block index, and then we basically step our pointers by our block index. So each thread is visiting a unique element from the memory. And then we go and we dereference our input pointer here. We take the X, we take the sign, and then we save it. And it's just basically, this is our our kernel grid, our kernel thread block. We're not using any shared memory. And then we're outputting 10 elements. So, and then here's like a slightly different rewrite of that. And basically what we're seeing here is that instead of having one loop where we do both the exp and the sign inside the body, we're doing two loops. Basically, we have fissioned out that loop into two loops. And so we are loading in A here, we're looping into it, and then inside the first loop body, we're taking exp, and then we're saving that to some intermediate buffer. In this case, that buffer would live in global memory. And then we're reloading that intermediate buffer, and then we're doing sign, and then we are saving it back again. So in all likelihood, this would be far slower than this because it just makes sense to fuse those and then not need to do that extra round trip to global memory. So, but yeah, this is what that would look like when rendered out into real kernels. So we take our A, this basically looks very similar to the original one, except we don't have the sign step. The sign step is down here. But the point is that this is a very simple deterministic process to go from our intermediate representation here to concrete real CUDA kernels. So that was a simple example of an IR. This is what a map.
Maybe Joe. Sorry to interrupt you, but like I had a question. There's also an interesting question from chat. So Joani's asking, like, there's sort of like a practical difference when you're doing rewrites between things that are like mathematically equivalent versus like equivalent roughly to floating point arithmetic on real GPUs. And so, like, do you take into account like numerical stability and like when, or generally when do you need to versus not need to? And doing
yeah. When we're doing the profiling runs right now, we basically just check that the outputs are within some tolerance for numerical stability. What I would really love to do is have some symbolic way of computing that ahead of time, and then just not need to profile any kernels that are not within that tolerance of numerical stability. We just haven't figured out how to do that yet. So we just, since we're already profiling the kernel, we might as well just check that the output is within that tolerance.
Okay. The other question I want to ask you was like sort of around like defining like just because like I'm a beginner as far as like search-based compilers go, but like typically the way I've seen this like within, let's say, deep learning compilers like Torch Compile is like you basically have some notion of auto-tuning where like there's like a very fixed set of decisions you need to do, and then you need to like iterate through everything and then see what's the fastest, and people sort of complain about compile times. That's probably so like just like in this regime, the set of decisions is very simple, but here the set of decisions is like relatively complex, and so I'm sort of trying to understand like basically, is this like rewrites to the IR or like how does this like work? Like it seems like more complicated for me to reason through.
Yeah. So you can kind of think of it as like auto-tuning on steroids, though, where basically instead of auto-tuning just like one axis of say tile size or something, our auto-tuning is on a million different axes at the same time. And so like one of the things that we can auto-tune is like auto-tune in this case is whether or not we should fission these loops. So whether or not this should be one loop or two loops. And so, the point is like we're doing these rewrites on this intermediate representation here. And then you're right, compile times are a real concern. What we're really going after here is targeting production. What we find is, we mostly get like 90-10, or we get like 90% of the speed boost with 10% of the time. And then to get that extra 10% of the time, you need to spend a lot more time. But within like 5 minutes or so, 10 minutes, we're able to compile like pretty fast implementations. But yeah, like I do see a world where it's worth it though to compile for say a couple hours, because if it does help your runtime at the end of the day, like if you're running the model a lot more than you're compiling it, then it still pencils out.
So a lot of this is like dependent on like how generic the outputted kernel is. So for example, if the kernel is like shape specialized, and then you sort of like you're running sort of like batch size and inference and prod, and you might expect different kinds of like batch sizes.
Yeah.
All of a sudden you're like, oh no, I need to recompile, versus like you compile all the shapes versus you write like one kernel that is shape independent.
So Absolutely, that would have been a problem, and this was like something that I realized would be a problem early on, and is something even that like people complain about with Torch. So what we do is we represent our dimensions symbolically, so they're not concrete numbers always.
Mm.
So what that means is you can have dynamic dimensions, and so batch size. Your batch size can literally just be a variable representing batch size, and that will be compiled into the kernels. And so if you don't want batch size to be fixed, you can just keep that symbolic, and then you're going to get a kernel that works with all different batch sizes. But if you're say, if your batch size is say fixed, then you don't need to keep it symbolic. You can just define like some concrete number. And the point is that we want to specialize these kernels as much as possible, but then still give you the levers to keep what needs to remain dynamic to keep it dynamic. Because you can imagine like, sequence length. If you're on like a prefill stage of an LLM, your sequence length might vary radically. And so you definitely want to keep that dynamic. And so, yeah, we just achieve that through keeping all of our dimension sizes symbolic.
Yeah, and presumably, like in practice, I would imagine that, like, for example, the output kernel that you show on the right would just have like sort of symbolic variables instead of like the where it says grid 1011, it'll just have like,
Exactly. Yeah. So we can make 10. We can, instead of doing 10 here, we can have it be like B, and then B is set at runtime, and you don't need to recompile anything when you change B.
I see also in chat, like Apaz is making the comment that you can also do shape dependent and pads, and then create a bunch of specializations to dynamically dispatch over.
Yeah,
I guess that works well.
That is basically then when we do our search, you're able to pass in some like example sizes as well that you want to target. And so say you want good kernels for shape batch size 1 and batch size 64, because those are like common ones that you might see. You can keep batch to be dynamic, so that you always will have the freedom to change the batch, but the search will be ran with those batch sizes in mind. And so when it goes to profile, it needs to make some concrete number out of that symbolic B variable. And so it'll pick one of your examples, and then you will get kernels out that work quite well for those.
Yeah, like this is gonna sound like a meme proposal, but considering there's only like a few models that people care about, then you could imagine that like you could have just like one giant mega cache of all the shapes and kernels people care about, and then just like have like one giga cluster produce them all, and then everyone else just like consume them.
Yeah. To have like some cloud where you can like connect to it and just have like a kernel cache or something. I've thought about that. Yeah, that would be a pretty neat idea. I don't know how willing people are to connect their compilers to a cloud, but it definitely, I could see a world where that makes a lot of sense.
All right, maybe enough digressing on my end. I'll let you keep going.
Sure. Yeah. So again, this is the matmul intermediate representation. Basically we just have two global memory inputs, and then we have a global memory input for our accumulator as well. But that will just start off as 0 because we want to initialize our accumulator to 0. So we have our A input, B input, and then what we see here is we actually have 5 layers of loop-ins. So in this case, the first 2 layers are the M and the N dimension, and then we have 2 padding dimensions in there. I'll get to why that is. And then we have our K dimension as our last loop in here. And so you'll see that basically we do our broadcasted multiply here, and then we are adding with our accumulator. And then basically, this isn't actually a great visualization because this stride is 1. This stride, it's rendered out as 1, but it actually is a special stride, which is an accumulate stride. And basically what that tells the codegen is that this last loop here, this K loop, shouldn't be parallel. This should actually be a sequential loop. And we should take this output here and feed it back in as the input. So we shouldn't have any sort of stepping. As we iterate our loop, we basically should just keep reusing that same accumulator. And that's how we are able to do like general purpose accumulation. So we actually are replacing like max reduce and sum reduce with this form, because this allows us to do like any form of accumulation. It doesn't need to be like sum or max. It can be like super complicated, modulo reduce or something, whatever. And then, we have our loop outs. And so we have our 2 padding loop outs, and then we have our N loop out, and then our M loop out. And you can kind of see how it goes like outside, like this loop out matches with this loop out, or this loop in, and this loop in, and this loop in. And then it sort of like goes from like outer to inner, where the loop outs and the loop ins all correspond with each other. And so when we actually go and we code gen this, we get this kernel here. This is just a really straightforward matmul kernel. Here we have our grid. So we're just assuming a square matmul of M and N equaling 64. We don't use any SMEM or anything, and we're not using our thread blocks. So in practice, like this would be quite slow, but just for demonstration purposes, we have our input buffers coming in here. We are stepping our pointers by the M and the N strides. And then when we actually go and get our final input pointers here, we initialize our accumulator here. You can see kind of some like compiler remnants here, because not for some reason, it's initializing the accumulator as an array, and then it's doing this like generic array copy operation, but it really is just one number, and it should just be like setting it a single value. But yeah, we will. Honestly, CUDA compiler might get rid of this by itself. Otherwise, we'll just have to touch up our code gen so that looks prettier. And then this is our K loop here. So we're actually looping through the K dimension. It's 64 elements long. At each stage, we're basically grabbing new input elements here by stepping. This is our stride. And so, for this, I think this is B. We are stepping 64 elements each time, because we're stepping like over a row each time as we go down the matrix. And then for loop A, we're just stepping over columns. So we're just stepping one element. And then, we have our dereferencing here, and then we're doing a multiply, and then we're doing an add with the actual N is the accumulator here. And then we're setting N to the result here. And then once we're done with that, we stepped M. M is our output pointer. So we actually have to set M to the accumulator result. And so, we get 4096 output elements here. So standard matmul. But this is how it sort of looks in IR versus actual CUDA. So I mentioned we use egglog, and we use an egraph as our underlying data structure. It really provides a way for us to build this search space in a pretty robust way by writing these rewrite rules. So you guys should absolutely check them out. This is their website, egraphsgood.github.io. And then there's like a really cool demo here. So if you go to the demo link, like you can basically just pick a demo and then you can run it, and it'll show you like a visualization of what an egraph actually looks like. And you can just modify this code here and it runs right in your browser. Super great. I would highly recommend this. And so let me close that. Yeah, so we use egraph, and we basically, when we take our IR in this form, that is basically written by the front end, generated by the front end, this very naive IR. We render that into egglog code, which is like kind of a dialect of Lisp, you can think of it as. And then we have our rewrite rules written in this egglog language. And then we run it for a certain number of iterations. And basically what it does is it takes every rewrite rule and it applies it in every possible order to build out this search space here. So there's like a very common problem in compilers known as the ordering problem, which is to say, like, you have a couple different optimizations that you can do to a given program. And you can either do optimization A first or optimization B first. And maybe the best route is you do B first, and then you can run A on the output of that. And so really what you'd want to do is go B and then A. But ahead of time, like, that's very dependent on the program. Sometimes it should go A, then B. And there's no right answer here. And so what we do using this thing called equality saturation, this technique called equality saturation, we're able to apply all of the rewrite rules simultaneously and build out this big search space. And so it really doesn't matter if A first and then B would have been optimal, or B first and then A would have been optimal. We try them all in all orders, maybe A and then A. Maybe there's a sequential application there. And so really what this looks like is, in this example here, we actually see 4 E-graphs, and you can see they are similar to directed acyclic graphs, but they actually have an individual node can actually have like multiple nodes inside of it. This is called an E-class, and then there's like E nodes inside it. Again, go to this website here. It gives like a really great explanation of E-graphs, but it's a very robust way of doing algebraic rewrites. And then here's like what those rewrites actually look like. So we have associativity represented by this very compact rewrite rule here. So we have like A plus B plus C. And basically what we're just saying is we're rewriting A plus B plus C to be A plus B plus C, standard associativity. And then we have another rewrite here where we're taking anything divided by 1 and we're setting it to itself. So x divided by 1 always will equal x. And so we can just eliminate the divide by 1. And so, yeah, egglog is super great. It allows us to rewrite, to do these very nuanced rewrites in such a compact manner. And then basically string together these very simple local rewrites to form very complicated rewrites in ways that we can't possibly predict beforehand. And so the sort of core Luminal rewrite set only ends up being like 20 or 30 rewrites. And I don't expect it to ever really grow much larger than that, because we don't need to have complicated rewrites. If we want to do complicated rewrites, we can string, the search naturally will string together a bunch of simple rewrites. So yeah, one of the common optimizations we see here is kernel fusion. I think a lot of people in this server probably know, this call probably know what kernel fusion is, but just in case you don't, basically most of the power spent on a GPU is moving data around. The compute is really fast, the memory is really slow, and so we ideally want to move around stuff as little as possible. So if you move stuff less, you will run faster usually. So if we go back to this like sine and then exp2 example, unfused, we would just load the original input. We would do the sine, we would write it to an output global memory, and then we would read it back in, and then we would do exp2, and then we would write it back out. And so we can kind of see what that would look like here on the left, assuming you even have high bandwidth memory. You would be doing a read from high bandwidth to your actual streaming multiprocessors, and then writing back, and then reading again, and then doing the second operation. And instead, what we can just do is we can load the tensor, and then we could, while we're in the streaming multiprocessor, we don't ever need to actually save the intermediate output. We can just immediately do all the operations possible right in the processor and then save the final output. And so, that ends up taking usually like half the time of the naive case. So this is what it kind of looks like in practice with some graphs. Here we have a pretty complicated example where we're actually, we have like some subtraction at the beginning here, and we're multiplying by a very particular constant, and we're loading in like another input, and we're doing like sine and then multiply, and we're actually doubling the original input by adding it to itself. We're doing all this like crazy stuff here, and naively this is like 8 kernels or something, but our compiler is able to immediately fuse this all down because it's just operating element wise. So we're not actually doing any sort of like cross element complicated movement. And so, yeah, we can just very cleanly fuse that down into one generated kernel. And then we basically just load 2 inputs, and then we write 1 output, and that's it.
Joe, for what it's worth, I kind of like your explanation of like you can think of like fusions as like rewrites to your model where you change the location of your loads and copy to devices. I think that seems obvious in hindsight, but like I think you put it quite nicely. But the main thing that like stood out to me, and also to Joni, I believe, which is that like some of the ops here are like mathy, like signs,
yeah,
and others are systemy, like metal copy to device. And I'm sort of like curious how you think about like these things, because like at least what you talked about with e-graphs, like it seemed like very like very like mathy transformations? Is it sort of like all the same? Or yeah, any comments there?
So we basically insert like the system-y ops after we're doing the rewrites, and so once we want to actually like generate the code, you can go through like the purely mathematical graph, and then pretty deterministically determine like where we should put a copy to device and where we should put a copy from device. That is sort of like a second pass after the math rewrites are done, and so you're right, like. I think the actual search, like when we actually do the search, it looks a lot more like one of these graphs or one of these graphs here. And so it's much more in math space. And then we're doing like, actually, it's not really shown here, but when we're going from this representation to this representation, we have to insert our actual loads, our system ops.
And so sort of related to this, like if you're calling specific hardware intrinsics, this would also be like post-processing the math graph where you're like, oh yes, I call this ASM, etc.
Yeah, no, exactly. And then we have like actual like hardware specific rewrites as well. They're not like super common, but like say you're able to basically do a rewrite from a pattern where you're doing, I don't know, like a 16 by 16 matmul. And we know we're running on a GPU that has a 16 by 16 tensor core. Well, we can just put that rewrite in so that when we're doing the search process, we can swap out the matmul pattern with one tensor core intrinsic. And that's obviously device specific, because if you go across devices, like this stuff changes. And then basically, there's not a whole lot of rewrites you can do past the tensor core insertion there. So that would tend to happen towards the end of the search process. But yeah, that's basically what you can do with like device specific type rewrite stuff.
Got it. And so, but then the mathy stuff is like accelerator, like agnostic and portable.
Yeah.
Okay,
It's like almost always better to not do x divided by 1 than it is to do x divided by 1. It doesn't really matter what accelerator you're on.
All right, sounds good. Thank you.
Yep. So so something we kind of I thought was pretty cool we achieved like maybe a month or two ago was we basically looked in our search space. We wrote out naive attention in the search space in like this naive IR, and then we ran our search, and then we saw that the output of it ended up being flash attention. And so we basically just through like dumb search and profiling were able to discover flash attention because our rewrite rules were generic enough to expand this search space so big that it contained flash attention. And so yeah, on the left hand side here we see the IR for naive attention, and then on the right hand side we see it for flash. Obviously there's like a lot less loop in, loop outs. There's just basically you can say that like one of these groups of like 3 or 4 ops tends to be its own loop. If you look like really closely, you can kind of see that there's like a loop in, loop out pair there. But you can see that, there's far fewer loops going on here. And it's because basically these attention loops have been fused into one single pass through the keys and values.
Actually, this seems pretty sick. I just want to show you one quick thing.
Sure.
I'm gonna actually share my screen. Yeah. So I'm very curious to hear your thoughts on this, because this is something like I've mentioned in so many presentations. So this is like the flash attention to open review, and then someone asked, where is it? Compiler. Yeah. So do you think a compiler could realistically generate flash attentions to? What sort of cost model could be done? And then, I think the feedback was that, well, compilers can generally perform fusions. However, optimizations that require mathematical rewriting of the same expression while maintaining numerical stability are generally harder. And effectively, no one really does this. Like, effectively, I think the way I've seen this work in other deep learning compilers is like via pattern matching, where you go like, oh yeah, so this seems like an attention pattern. Let me sort of like splat like the fast kernel code. And so I'm sort of curious, like it sounds like you have a sort of fairly unique take here, so I'm wondering if you could say a bit more.
Yeah. So I think, to my knowledge, when we actually did this, like to my knowledge, I don't think anyone else was able to do this. Basically, this, in fairness, this does require like one maybe slightly non-generic rewrite, which is to do like an online softmax rule, but it is a pretty I would say it's still a pretty generic rule. It's not very hand coded just for attention. It's just like a good optimization to basically like shrink a max loop to an online max loop. But yeah, so basically what we found though is that like there are like, I think it's almost like 12 or 14 different different rewrites that need to be applied in sequence to go from a naive attention to a flash attention. And they're all pretty much generic rewrites here, except for that online max rule. But it really is just like you just let the search run for a really long time, and then it gets there because you can't really like guide the search. I mean, if you guide the search, in my mind, that's like a little bit of cheating. But yeah, so like it really is just like you take these algebraic rewrite rules, and that allows us to do this sort of like mathematical rewriting as opposed to just like pure system level rewriting like kernel fusion and stuff like that. And then as long as your compiler is able to string enough of them together, and flash attention does lie in your search space, then it should be able to eventually find it. Now, flash attention 2, I haven't read too much on, so I don't actually know the difference between flash attention 1 and 2. And I know they have now a 3. And so, you know, I don't know, maybe we'll discover flash attention 4. But
yeah, so 2 is more of like system level optimizations on top of like 1, so it's more incremental. 3 is more about like using new hardware intrinsics.
yeah.
So like you would just probably need new rules that are like, oh, use TMAs, use worker consumers, like so sorry, like producers consumers, like
the worker consumer stuff is like very interesting to me as well, because you know, we haven't really got into like doing that in our rewrite rules yet, but like I think they're using something like ping pong attention, where they're doing like something produce it and then something else consume. It's very interesting, like warp specialization stuff. But yeah, I that's definitely in the future.
So yeah, I'll pull up your screen again.
Cool. Awesome. Yeah, so back into it. Here's the naive and the flash. We did a little bit of a announcement post, and basically we have like a flash attention demo directory inside of our open source repo, and so you can just like run that example, and it will do the full search for you. If you don't have M1, it'll basically just expand the search space and then validate that flash attention is inside the search space, but it won't actually do all the profiling. But yeah, you can run that. And this was sort of like a breakdown of some of the steps that needed to happen for this translation. We did a whole bunch of loop fusions. We did that online max rule that I was talking about, some other loop fusions, and then we're able to do loop swapping because of the way we represent strides. As long as you can basically tie strides of your inputs to the actual loop that is being swapped, you're simply able to just like, you know, it's basically the same way that PyTorch does transposes without actually doing transposes. Like they can transpose the dimension. Oh, something's going on outside.
Sounds like you live in New York or something. Just from the sound.
I don't know. Pretty quiet usually here in San Francisco, but I guess not. Yeah, but we're able to do like loop swapping pretty easily there, and then we have simple tiling rules where we basically split a single loop into 2 nested loops by some constant factors. So for us, it's usually 8. And then we can do like loop fission, other swapping, and then there's like 10 more rewrite steps here that I don't want to like go through because it'd be just too confusing. But basically, suffice to say, it's just a bunch of these like really simple rewrites stacked in sequence. And yeah, there is a generated version of the kernel. It's just pretty standard flash attention. You know, very naive flash, like a naive version of flash attention, I should say. And then, yeah, so then we do some deterministic optimizations afterwards, after the search is done, that we basically know if we do these rewrites that the output kernels will always be as fast or faster than the input kernels. So we should just always do them. So basically, we can go through like reusing buffers. Obviously, there's no reason not to reuse buffers. If you have like some buffer that has been produced and then consumed and it's not going to be consumed again, you can use that space. And then, yeah, basically we can reuse that buffer pretty deterministically. And so this is sort of like a visualization of that. Like we have a buffer and then, buffer 1, buffer 2, buffer 3. By the time we need to write to buffer 3, buffer 1 is already done. We're not going to use it again. So we should just reuse that. That's pretty deterministic. Then the other way would be like queuing kernels. This is like sort of like what CUDA graphs does. We don't want to have the CPU be bottlenecked by dispatching kernel after kernel. And so basically we dispatch them all at once. We render them all out. We assign the input and output pointers, and then we put them all on a big launch queue, and then we just launch them ahead of time. And so again, like there's no reason not to do these. And so this doesn't need to be part of a search. This is basically just like some post-processing passes that we do. And yeah, this stuff works very similar on both Metal and CUDA. So most of this logic is shared across like Metal and CUDA. And then, yeah, like this was always designed for me. I cared most about inference. This was designed to be inference first. I had like given no thought to training because I thought like training would just be like way too complicated to implement. However, I realized that like, training is really just a fancy form of inference. Like there's some like complexities with sort of like nickel collective operations and stuff like that. But really, especially on single device, doing training, what we do is we consume a forward graph. We have a little tiny autograd engine that, because we're only using a very few number of primitive operations, we're able to derive a backward graph pretty simply, just using the chain rule. And then we fuse the forward graph and the backward graph together into one unified forward-backward graph. And then that all happens before the rest of the compilation passes. And so we get the rest, we basically are able to fully compile both the forward and backward graph sort of like for free without any sort of additional compiler logic. But yeah, so this was kind of like a neat extension that we were able to add. And also, we want to keep Luminal as extensible as possible. And so we're able to actually add this training in sort of as an external crate plugin. Which again, to my knowledge, I don't believe I know of any other ML framework that's able to add in training as an external extension. It's always usually a core part of the library. So I think that's pretty neat. But yeah, so and in this tweet, it was pretty cool because our representation is so simple. Our autograd is only like 150 lines long, so we can fit it into a tweet. So yeah, that's sort of a summary of where we are right now. And then sort of as far as future plans go, we want to add in more backends. Right now we support CUDA and Metal and CPU. We want to add in AMD. We want to add in TensTorrent. We're working on a TensTorrent backend right now. We'd love to add in Grok. If anybody works at Grok, reach out. I'd love to work with you guys. And then TPUs would also be really cool to support. And because most of that is just, we change like the last code gen pass and most of the search minus a couple device specific rewrite rules, most of the search remains the same. This shouldn't be like a tremendous rewrite or a tremendous effort. Already, like a lot of CUDA Metal stuff is shared logic. And then we want to go distributed. So we're like super focused on single device right now, but we want to support like large cluster workloads, or at least single host workloads, single host multi-device workloads. And we should be able to derive a lot of these topologies or do all these topologies ahead of time as part of the compiler. And so as long as we're able to make the compiler aware of like the data latencies device to device, then it should be able to optimize with that in mind. So that can be part of the basically part of the cost model. So yeah, deriving data pipeline tensor parallel topologies is really cool. RL, I've been doing a little bit of RL experimentation. I don't really have an RL background, but I think it'd be really cool if we can do it on graph. At least certain continuous environments you can put on graph just with our primitive operations. I know XLA has done some work on that as well. I got to look into that more, but that would be a really neat thing. If anybody's interested in that, please let me know. And I don't know, maybe if Sequoia fundraises us, we'll build a Dyson sphere. But yeah, and then sort of on the business side of things, we have a cloud. We're building a cloud. Basically, we're going to take the unoptimized compute graphs. You can upload them. We will do the whole compilation process for you on our cloud, and then we'll give you back a serverless inference endpoint. And so if you want to upload your model there, we'll run your model totally serverless. And our core technology allows us to do that, better than other serverless clouds with no cold start times or anything like that. And you don't need to figure out Docker containers or hand optimizing or hand engineering any sort of setup there. And yeah, come join our cult. That's our GitHub link in the slide. And we're really, I think, pushing into what takes other softwares orders of magnitude more complexity and line count to do, and we're doing that with our sort of unique approach to things. The simplicity of the core library really allows us to do things that would take quite a bit more engineering effort in other libraries. And then we're building, again, the fastest, simplest ML cloud in the world. So reach out. There's my email. And that's it. I think I've made time. 1 minute to spare.
Sweet. Hey, Joe, this was great. Thank you so much. I guess, yeah, like there's a bunch of more questions in chat. And folks, if you have any more questions to Joe before he heads out, just please post them now. I guess one thing I'm curious about asking you is like, obviously like a big part of it sounds like you're pretty big on open source. Like I just saw like most of the compiler is like open source. And so I'm sort of curious, like where do you see good collaborations being an open source versus like more closed source? I guess you do have to pay the bills in some way. So I'm curious if you could speak more to this.
Yeah. So, Luminal was my hobby project for a while because of this question. I was like very hesitant to try to start a startup around it because until I can have like a good answer to the monetization question, I think a lot of other open source projects also struggle with this question. And so, what we really kind of came up with is like a very Vercel style model where the core and basically everything you need to run locally is open source. And that includes the compiler and the framework and all that. Basically anything you need to get running on your own machine. And then to do deployment, production deployment, cloud specific stuff, that's sort of our business. And so you take your compute graph, and when it's time to actually deploy, it's just going to be like a really simple upload. You upload that, we compile it, and then we have like our own cloud runtime pretty much. And that handles like job scheduling and workload batching, auto batching, and workload merging, and all this other fancy cloud specific, deployment specific stuff. But yeah, as far as the core compiler technology and the core framework and everything else, I really want that to remain open.
Sweet. And for what it's worth, like you're more than welcome to share like more technical updates on the server if you want, like your own channel. Just let me know, because like I actually really liked how like simple your explanations of rewrites are, and so if people are interested in like sort of learning about ML compilers. Indeed, like ramping up on million-line code bases is usually like a tough sell. So,
awesome. Right. The goal is we want to be able to keep the core at least learnable in like ideally an afternoon, but at least right now a weekend.
Sweet. Okay, I see 3 more questions, which is I'll add to this question. So you mentioned like you mentioned with a smile at some point that hey, like the compilation can take a while, and then a pause is talking about like, well, like what are good ways to prune the search space. And I'm sort of curious, like what do you consider to be like an insane amount of compilation time? Because it's all relative, right? Like if you say, so how many GPU hours or like MacBook hours are we talking about for like, let's say the flash attention work, for instance?
Oh yeah, if the I'm trying to remember an exact number, but I don't remember an exact number, but it was like 5 to 10 minutes for flash attention. It
Oh,
wasn't
I
like
see.
extraordinary amount of time.
I was expecting you to say days or hours as well.
No. So,
Okay.
yeah. But I mean, again, flash attention is like a small part of a large network. And so if you wanted to do an entire model, what we're basically doing right now is we're building in a system where you have like repetitive parts of a network. So picture like an LLM. You have like 32 repeating layers and they're all the same operation. And so you basically just put like a chunk break in between them. I call it like a chunk break. And then we basically just compile one of those layers in isolation. We don't need to like jointly compile the entire network, because jointly compiling the entire network might take like a week or a couple of days. But compiling a single layer is done in under 10 or 20 minutes. So as long as like we do that and sort of chunking, that really helps. And then as far as like speed, we are working on getting like MCTS actually working very well. I think MCTS, Monte Carlo tree search, will help us explore this search space much faster. We probably only get away with exploring like 1% or less of the full search space if we use MCTS. And my hope personally is that as we improve the search, it runs faster and we do things like MCTS, we can end up exploring, or we can end up basically removing these chunk barriers and then get back to jointly compiling the entire thing at once, because then that requires zero hints. Basically, chunking is kind of like hinting from the programmer's perspective.
And so like this is related to Paz's question in chat, which is like, do you view things like alpha beta pruning as cheating or not really? Like it's all like anything that prunes the search space is fair game.
No, yeah, I think it's as long as it's not like very, very specific to a given model or a given hardware, I don't think that's cheating. That's just kind of like pragmatism at that point.
All right. So, okay, I see an interesting question by Meep, which is that like, I'll sort of rephrase the question for what it's worth, Meep, so I apologize. So like, I mean, you can sort of like, you can encode any computation as like, with like Boolean algebra or like CNFs, but like, obviously like no one does this. And so what do you think is like a good trade-off between like the sort of obviously most minimal ops versus hey, here's like 20 ops or 50, like for example, Torch compile is like 50 in your case. I think you mentioned like 20 or so. How do you think about the trade-offs when picking the number of primitive ops?
I'm not sure there's like a right answer, but I think like you don't want to get too egregious with it, because technically, yeah, you can get down to like 4 ops or 3 ops or some like really small number, and then your graph just explodes. I think it's more just a question of like pragmatism. What creates a small enough graph to be like reasonably searchable and reasonably manageable, and you should be able to look at it and still kind of work out what it's doing. It shouldn't just be this jumble of primitives, but it shouldn't be like too many specialized ops. And like my whole thing was like, I don't want ops that are only ever used in like one kind of model. So I don't want like a convolution op, or I don't want like an attention op or something like that. As long as like the primitive operations we have are broadly applicable across most or all ML, neural network workloads, then I'm fine with that.
So is like the core insight that like you could presumably have only like a single NAND op, for instance, and that's it. But then the size of your graph is massive, and a lot of these rewrite rules are presumably like quadratic algorithms.
Yeah.
And so that's what you mean by the size of your graph blows up?
Yeah. You don't, if you basically wrote llama in our primitive graph today, it would be like about 1,000 or a couple thousand operations. And like sort of writing rewrite rules to match on those graphs isn't very difficult. Like the rewrite rules, they'll ordinarily maybe match on like under 5 operations, because that's enough to describe some pattern that you want to grab and replace. But if it were like, something more simple, Boolean algebra or something, like your rewrite rules would have to get way more complicated. And then actually like matching on those rewrite rules would take much longer, and you would need to probably match on far more of those rewrite rules. And so it's like, it's just like an exponential explosion in terms of like graph complexity and search space.
All right, so I think I'll just take one last question. Where was it? Okay, so a cyclic mentioned something interesting, which is that like a lot of your search rules emphasize searching over mathematical things, but then you often have this assumption at the system level that like you know what is the right thing to do. Presumably, like as GPUs get more complicated, like figuring that out might not be super trivial. Like basically, what is the right, like what are the right hardware intrinsics to call? Kind of like where a lot of like human kernel authors spend a lot of their time. And so I'm sort of curious how you view that evolving, if at all.
Yeah, no, absolutely. You know, like I said before, you know, you could have like a rewrite rule that just finds the 16 by 16 matmul pattern and then insert like a tensor core intrinsic there. You can pretty cleanly merge in most of this like hardware level rewriting into the actual like mathematical rewriting. It basically exists in the same space. I mentioned before though that like there is somewhat of a difference where we actually insert copy to, copy from type things. I would kind of split those into two different kinds of system operations though, where on the one hand, if you have like tensor core intrinsics, those are kind of optional to use. And so those should be put into the search space because you don't know necessarily if it's better or worse to use some of those hardware intrinsics. Whereas, you know, copy to, copy from, those sort of just have to be there. Like you need to copy the data over to the GPU memory to actually use it. And so that really shouldn't be in the search space because that's not really optional. But yeah, to the point that like, I do believe that you should put system level intrinsics in the same unified search space as your mathematical rewrites as well. And definitely like this is one of the key motivations for Luminal is that like if you look at the complexity level between Ampere and Hopper and Blackwell, it's like these things are just getting more and more complicated and it's less and less obvious when you should use different pieces of hardware. And so our solution is just like put it in the same search space and search over it and see what one does best.
That's interesting. You're saying search is even more relevant because like, okay, just because like fundamentally the set of humans that will be able to do these trade-offs also will get smaller over time as opposed to increase.
That's right.
Okay, I lied. Maybe I'll ask you one last question. Have you thought about like also adding like collective ops? And if so, like do you sort of like foresee like fundamentally more challenging trade-offs, or do you think sort of the same idea will work?
By collective ops, you mean like nickel, like multi-device?
Yes.
Yeah. So that was one of the things that we want to do distributed here. We want to have a graph that doesn't just exist on one device. It's just like this logical compute graph. And as part of like a search parameter, you're basically just inputting the device setup that you have. And then in the search space, it decides where it's going to put those device breaks. And then wherever those device breaks are, like that determines what your collective ops are. And then, you know, it basically decides like, okay, I have like say 2 GPUs, keep it simple. I have 8 layers. Maybe do I want to put 5 on device A and 3 on device B, or maybe I want to do 4 and 4. And then I have like some copy op in the middle there. Like, again, to that point, like, I don't think there's a right answer. I think that you just have to search over it and find it. Like, I'm very much a proponent of the bitter lesson in these types of cases as these setups get more and more complicated.
All right. Well, thank you, Joe. I think that you know, like that's like maybe a cool way to end things. So thank you so much for coming, folks. Like, I think if you want to talk more with Joe, he left his email earlier. They have their own Discord. Feel free to ping Joe on our Discord as well or on Twitter. Yeah, Joe, pleasure seeing you. And I guess, folks, tomorrow, on that note, we'll be talking about like multi-GPU programming. So, and I'll be at ICML if anyone wants to say hello. And thank you, Joe, and thank you for everyone watching.
I might be at ICML too. I haven't decided yet, but I might be there.
You should come. You should come.
Awesome.
All right.
Sounds
see you guys
great.
soon.
All right. Thanks. Have a good one.